Okay, everyone, fantastic. It's 5 o'clock. Let's get started for 2 hours of fun. So today we're just going to finish up the last content from Unit 6, which involves Project 2. And after that, I'll invite a few questions. We have to time box that. But yeah, if anyone has questions for Project 2, you can put it in chat or ask me in this room. And then we'll move on to Unit 7. So Unit 7 is all about data, how to manage data, big data, small data, and how to do inference on data, how to infer things with machine learning and techniques like this. So we'll get through a chunk of that today and tomorrow. And then you can expect to see the sort of very specific content relevant to Project 3 we'll cover on Monday. Which is the decision trees and random forest approach for machine learning. Yeah, but you guys are probably all focused on Project 2 at the moment anyway. So, okay, let's get cracking. So Unit 6, Unit 6 is, maybe we can put this over here, is all about discrete event simulations in Monte Carlo. Okay, and we've talked to death a little bit about how to do random number generation, how to create a a discrete event simulator in Julia. I hope your Project 2 is coming along nicely now. I hope it sort of made enough sense that you could sort of replicate it and build your own simulations. But as you can see, the idea of one of these simulators is to create one of a number of possible trajectories in time, some possible futures, some possible realizations of trajectories of a system throughout time. Okay, so we'll just skip over some of the content that we've covered. So that's sort of one sort of variety of Monte Carlo technique. Okay, it's in a way it's kind of naive or trivial Monte Carlo. I think I alluded to in the beginning. Some people even just call it's a sampling, a statistical sampling simulation rather than the Monte Carlo simulation, because what you can do in the kind of simulation we've done is you can actually start with an initial state and really simulate directly with direct sampling a trajectory. Okay, so if you look at this equation here, that the mean of G is 1 on n, or the expectation value of G, let's say, is 1 on n times the sum of G evaluated in a bunch of instances X. So when we talk about X in this case, in this equation, okay, X isn't, in our event simulator, X isn't just the state of the system, okay? X in the case of the event simulation is includes the entire trajectory, okay? So with our program, we can generate a trajectory directly. And we can generate another trajectory and another trajectory. And we can do this n times. And we could, for example, find the expectation value of some quantity, perhaps something that varies over time, like the number of people in the queue. There would be some transient. Let's say you're open and nobody's in the amusement park or whatever you imagine the system to be. The queues are empty. You can imagine there's some transient, and the queues grow and grow, and then they sort of top off at some level. Okay, but so what we do is we don't have this nice smooth thing. We have this sort of bumpy ride as the queues going up and down, like the plot I showed you a little bit earlier today. Yeah, but if we take enough averages of different realizations, we could imagine plotting them, the mean as a function of time or something like that. What we've actually done, or asked you to calculate in Project 2 is a little bit more not advanced, but it's a little bit more than just this. What we've done is we're not talking about taking millions and millions of trajectories and averaging them. We're taking a single trajectory and letting it evolve over time for a very long time. And because it's an ergodic system, one where ergodic means that you can hop from any one state of the system to another. Then there's a proof about ergodic systems, which says as you let the system evolve, it will reach a stationary state. So when we say stationary, what we mean is the probability distributions stop evolving. But within a certain realization, of course, the numbers in the queues are going up and down. It's not truly static, but on average, the distributions of the number of people in each queue has reached a kind of equilibrium, okay? And, you know, there's a lot of mathematics and interesting facts about such systems, things which have detailed balance or not, and things like that. And you can break things up into different categories. But yeah, if we just think of this equation we got here, you know, naive Monte Carlo is when you can just directly sample X, whatever X is. In the case of project 2, it's actually a complicated thing of the state as a function of time, that is X. But it could be something simpler. It could just be, you know, you want to roll a dice with numbers 1 to 6 on it, okay? So with Monte Carlo is a more complex thing. Like I said, we have that ergodic theorem, which lets us look at stationary states. We've got another thing here called importance sampling, okay? So this is a really important thing. Imagine you wanted to look at really rare events that happen, such that you may have to do millions or billions or trillions of simulations to find one of these events, okay? So you're looking for, you know, the 1 in a million year flood that's going to decimate Brisbane or something. What you can do is you can make the certain unlikely events that might occur. For example, let's say we're looking for queues of greater than size 100 or something. What you could do is you can bump up the probability of people entering queues, okay, in your simulation. But when you're doing this sum, see this expectation value of G? What you have to do is you have to account for that bump in probability by dividing by a larger number later, okay? So at the end of the day, what you can do is you can create an equivalent system. It has slightly different dynamics. It might be sort of pushed towards certain situations. But you also account for how much you've forced it towards those situations over time. And so you account for this probability and you divide by that and assign a weight to that realizational trajectory such that it's, you know, it's less important or more important depending on those weights, okay? And in that way, you can actually explore the space of rare events, for example, and actually get some estimate of how likely the 1 in a million event thing is with only doing, say, 1,000 trajectories, okay? So that's sort of an example that you can do here. One pet example of mine would be something called quantum Monte Carlo. So in quantum Monte Carlo, you're looking at not just the evolution of probability distributions over time, but more or less wave functions, how wave functions are evolving. Generally, you're applying it to the problem of stationary quantum systems, like ones at thermal equilibrium. But nonetheless, what you have is you don't have like this positive definite probability distribution. You actually have this complex space that you're trying to evolve. And you're kind of walking through this sort of state space in the wave function, and the weights that you come up with can actually be complex numbers. Okay, so you can have like a complex number times, you know, the result from this trajectory plus a different complex number times the result from some other trajectory, and it all averages out to the thing that you want it to average to. Okay, so you can do some quite exotic things with Monte Carlo techniques. Generally, probably the most important class of these things are Markov Chain Monte Carlo methods, okay? So these are often used in Bayesian statistics, but also physics and a variety of other subjects. I feel like I need to press Control F5 here. Give me a second. Yes, there we go. We have more equations. Brilliant. Okay, so in a Markov Chain Monte Carlo simulation, what you have is you might not be able to roll the dice. You might not be able to generate one of these X's with any probability, okay? You know some things about the statistical distribution, but you don't know exactly what the statistical distribution is, and you don't have an algorithm for generating a sample. So what can you do? Well, if you know something about the shape of the distribution, you can actually use Markov Chain Monte Carlo to guide you to this thing. So the example we're having here is we have some function of X. In the case we've got here, f of X is proportional to e to the minus lambda X. So it's just an exponential tail. Okay. And there's some constant 1 on K out the front. Okay. Now, in this case, analytically, we can integrate e to the minus lambda X and get 1 on lambda. Okay. And we could normalize f of X such that it is actually a probability density function. We could do that analytically in this case. In general, when you have a more complex system, think of your Q simulation or something, you can't really just sit down with a pen and paper and do an integral and calculate the normalization constant. But you might know, for example, the relative probability between two different states, which I'll talk about in a moment, okay? So, yeah, so generally you'll have this proportional to situation. And this situation comes up in a couple of scenarios. One is Bayesian inference. We're going to cover that. My background's more in the kind of statistical physics kind of regime. So in statistical physics, when you're thinking of systems at thermal equilibrium, I mean, what does that really mean? So if you have a system at thermal equilibrium and you're kind of looking at it, there's only so much energy here. There's that, like, you know, your material, let's say you're looking at a gas or a solid or a magnet or something. There's only so much energy in the system. And so, you know, the expectation value of the amount of energy depends on the temperature, for example. Okay, you increase the temperature, you increase the energy, or vice versa. What you do know is that you want to maximize entropy, and the state that maximizes entropy at thermal equilibrium is the one where states of different energies are related to each other in probability in a specific way. Namely that the probability is proportional to e to the minus energy divided by Boltzmann constant times temperature. Okay, E over KBT. So our lambda in this case is 1 on KBT. Okay, so in statistical physics, you'll often come up with this thing, and we actually normally call it beta. And you know the microscopic details of the system. So if I tell you the state of the system, I can tell you the energy. You know, if you give me the velocity of the atoms in an ideal gas, I can, you know, go half mv squared and get the kinetic energy and add that up, for example. And if you compare two states, you know that the one with higher energy is going to be less likely. But how much less likely depends on the difference in energy and the temperature. Okay, so if you want to use Markov Chain Monte Carlo, you can use this fact and you can actually find the states at thermal equilibrium using the Hamiltonian or the energy sort of landscape and this sort of Metropolis-Hastings algorithm, okay? So this is an algorithm, I don't know if you remember, but in an earlier lecture, I mentioned Metropolis and Hastings and Ulam, and maybe another one, were the first ones using the ENIAC computer to do these kind of Monte Carlo simulations, okay? So this comes from right from the beginning in the 40s and 50s as they're trying to simulate nuclear bombs, mostly sponsored by the US Army. Yeah. Okay, so, you know, in this way we can get results without having to do any calculations of this number K. So the Markov chain, a Markov chain, as you probably remember, is where you have some series of steps. You can go, from state A to state B with some probability. You might stay in state A with some other probability, or you might go to C with some probability. And there's a matrix. It's a linear kind of process. There's a matrix describing how to jump from one state to another. So the idea is if you continuously over and over and over and over again do this chain, eventually, because of the ergodic theorem, you'll reach the stationary state. And that stationary state will be a distribution from which you can draw from the distribution you're interested in. And that distribution that we're interested in will satisfy this kind of equation here, or this equation here. And you can set that up relatively easily. Like, for example, if you know the shape of this function, or in physics, if you know this energy landscape, you can set this up so that you always get the correct distribution in the end. And then you can draw samples, of a statistical physics system at a given temperature, or you can draw, or what we're going to use it for here is we can do some Bayesian statistics. So in sort of frequentist statistics, you just take measurements and you kind of say, okay, the universe is like this because we measured it. Okay. Bayesian statistics is all about this rule called Bayes' rule or Bayes' law. So it's a pretty simple thing. It's more or less the definition of this operation. So this is saying the probability of measuring A, given that we already know B is true, is the same number or the same probability as the probability of B given A, so the other way around. So knowing A is true, what's the probability of B, multiplied by the probability of A divided by the probability of B. Okay. So this is Bayes' rule. You can derive this relatively straightforward from just what the definitions of conditional probabilities are. Okay. But what this is useful for is if we had what we use this in Bayesian statistics for, let's say we had some measurement or some knowledge. We know, we've measured we want to know how tall Australians are. We've measured 1,000 Australians, their height, okay? And then we go and measure another 100, and we want to update the mean of what we think the mean or the estimate or the distribution of the height of Australians are. We can use Bayes' rules to take sort of our old probability distribution and mix it with our new measurements. Okay, so it's all about, to me, Bayesian statistics is all about using evidence. Okay, so you have some prior knowledge or prior information, and you acquire some new evidence. And what does that evidence mean? How does it impact the world? Some evidence will basically not change your understanding of the probability of the statistics much because it just agrees with what's there. And some evidence will be kind of surprising statistically, and it will change your view of what the underlying distributions would actually be. And the question is, how much? How do we do this rigorously so we don't count outliers too much and so on and so forth? Okay, so imagine you're an insurance company and every month you've noticed how many fires have happened in Brisbane, okay? So what you would say is this is probably some kind of Poisson distribution, because unless there's, a particularly proficient, prolific arsonist around, it's probably uncorrelated house fires, right? So it's probably a Poisson process, which is just things which aren't correlated to one another. And let's say, and what we're going to do is we're going to use this Bayes approach. So the posterior, which is the posterior, which is like, okay, let's go back here. This distribution is parameterized by theta, okay? So it's a Poisson distribution. The bigger theta is the sort of more fires you expect in a month, okay? And you have some initial prior likelihood. Maybe you just put your hand up, hand in the wind and say, oh, I think there's 5 fires a month in Brisbane or something, Okay. And then you go and add some measurements to that. The question is, how are we going to update theta to get a better value? Okay, so imagine we had some measurements of different months and the number of fires, and they look like this. Okay. What we can do is we can use these Bayes rules and set up a set of probability distributions. So this is the gamma distribution, the Poisson kind of process thing. Oh no, here's the gamma distribution. Sorry, that's the Poisson one. So that the prior, yes, sorry, the prior. This is what we think the distribution is at the beginning. This is our measurements, and we're looking at finding the likelihood and the posterior. So what we do here is we set up a Monte Carlo simulation, Markov Chain Monte Carlo simulation. So this thing here is looping over steps of the Markov chain. So you do step 1, you do step 2, you do step 3. This one here is doing the Metropolis Hastings algorithm on the inside. I'm not going to explain it, but I'm just going to mention that you can do it, and we can do it sort of statistically. And we can find the Bayes estimate of the of what we think theta should be given our measurements and our prior guess. Okay, so but let's think about this. We've got gamma distributions and Poisson distributions, and they're mathematically quite simple, and we can actually solve this problem analytically. So here again, I'm not going to talk about it at all. You only wrote all this up, but we have this this closed form, this solution, analytical solution or closed form solution of the posterior here. Okay, so beforehand our prior was this blue curve. We thought there was quite a few fires happening per month. From our measurements of the last year or whatever, we got some smaller numbers that we saw, and we can fit a kind of like gamma distribution to that data if we wished, which would be the red curve. And then if we put it all together, the final histogram that the Monte Carlo gives you is this black curve. So it's actually it's taking into account our prior distribution and the fact that we have a lot of measurements. Now, generally, in this case, the prior, there's only one prior, but there was like 12 measurements or something, which is why it's a lot closer to the red than the blue, but it is somewhere in between. I don't really want to go into that into detail. It's just an interesting sort of segue. So this part of the lecture is all about giving you context for what you might expect in future courses and future research, or what you could do with simulations in Monte Carlo. We've got another example for here, which is pretty relevant. It would have probably been more interesting last year. It's called the Seir epidemic model. Okay, so we're going to model something like coronavirus, where you have a population. S stands for susceptible. So you have susceptible people who have never been vaccinated or immunized or not infected. You have exposed people. So these are people who are, they have been infected, but they're not yet infectious. Okay. So there's a delay between, say, coming into contact with a virus before it sort of breeds up in your body and you start infecting the next person. And then there's infected people, which are the people, or infectious people, I should say, who can infect others. And then there's R for recovered or removed. Sadly, in epidemic modeling, it doesn't really matter whether you've died or you've recovered. You're no longer a person who will transmit the virus either way, because either you're immune or you're dead. So you're in the removed state. So this is an interesting set of things. If we look at the last two first, they're a bit easier to understand. This is we can do this analytically, but this is kind of the kinds of things you do with an event simulator like we're writing, where you go from a state with a certain number of people, S, E, I, and R, and we subtract one from E and add one to I. So that's a person who has been infected already and is becoming, been exposed, and they're becoming infectious. And this will happen at a certain rate. It's a statistical process. It's not everyone takes 7 days, you know, it might take 1 day for some people and 14 days for other people. So it's sort of random stochastic process, but it happens at some known rate, you know, it will happen within 2 weeks, roughly. So, you know, delta was probably, you know, 1 on 7 days in this case. So the rate at which this occurs is 1 on 7 days times the number of exposed people. If there's 1 million exposed people, you know, this process is happening quite often. And the same for the recovery or the removal. Deducting an infected person, adding them into the removed pile seems a bit vicious. It happens at some rate gamma, so that's how quickly do you recover. But there's this other one, just ignore the constants for a second, which is proportional to the product of S and I, okay? So if there's 0 infectious people, no one's going to get exposed. If there's 0 susceptible people, no one's going to get exposed. Okay, it's the product of susceptible people interacting with infected people, which causes infection or exposure, okay? So this is what makes this model nonlinear. There's some constants here. I won't dwell on them. But we could actually run a kind of event simulator like we've had before. And I'm not going to show you any of the code, but I will show you the results. And what you see is you start with everybody as susceptible in the population. And there's a few seeds. You've got a few infected people. So, you know, the exposed infected things, these don't start at 0. You're starting with some infected population. And then you're running a bunch of trajectories, not just one realization, but let's say 30 realizations, okay? What we're seeing in these straight lines are the mean of the results from the 30 simulations, okay? So on average, susceptible people become, you know, exposed, which is this blue bit. Then later on, they become infected. And they, you know, the greater the infected or the infectious people, the greater the slope of this downhill trajectory. But it's non-linear. What that means is at some point, you know, there's not very many really susceptible people left. So what happens is the effective reproduction rate of this virus can actually drop below 1. So what was originally very infectious, you know, might infect 10 people. But once 95% of the people have already been moved to the removed column, you know, you might potentially infect 10 people, but really there's only half a person that you're really going to infect because the other 9.5 on average, they're already immune. Okay. So this is a model that describes the way pandemics work. Pandemics tend to have this hump and then they go down, and it's because most of the population gets sort of infected and then recovers. What these yellow dots here are the final result for the final infected. So one question is, you know, how many people are actually going to get sick, for example? It depends mostly on this reproductive factor, but which is really going into these betas and down up here. Okay. And that's actually not a constant number. You know, it depends on some trajectories. You know, 95% of your population got infected, and other trajectories, 90% of your population got infected. And you can have really borderline cases where, you know, maybe it's 80% or maybe it's 3%, and you just don't know. It really depends on what happens. You saw in Queensland, we'd have just a handful of cases, less than 5 cases, and you're really down into the integers, you know, and it really does, you know, these 5 people that stayed at home and behaved, or is there like 1 person that went out and spread it to 30 people? And really that kind of, you know, stochastic process, really random events that are going to control the future of the whole trajectory. Okay. As I said, that's a bit of a flavor for some of the things you can do with these simulations. I wanted to open the floor for a few minutes. If anybody wants to ask me any questions about Project 2, please just put your hand up in the room or write on the chat and we'll answer them, and then we'll move on to Unit 7. Or if anyone wants to discuss what we just talked about also, please. Yes. Yes. Is it stored kind of like every other immutable variable, i.e. if you make a copy of it, it would copy all the data and not just like. Yes. So the question is about immutable structs in Julia. So the ones that are just called struct with no mutable in front. So they are just data, they're just bytes. So the computer will think of it as 16 bytes or something. And whenever you access it, it's just going to treat it as constant data. What it does in terms of copying it or not copying it is actually up to the compiler, but you can generally imagine it's created its own copy and dragged it into the function, and then it's gone and put it in an array or something. If the compiler knows how to do the same computation or the same algorithm without moving it and leaving it in place, it'll do it just because it's faster. Okay, it's just as an optimization. Yeah. On the other hand, the semantics of mutable structs is such that you basically, whenever you're referring to them, it's always going to act like it's a pointer or a reference to the data. Again, unless the compiler thinks it's faster and it's safe, you know, it's, to treat it as a blob of data, maybe copy it or maybe, you know, keep it on the stack or something. Yes, was that immutable or mutable? I don't know. The network parameter struct in project 2. Okay, immutable. Yeah, so if that struct had hundreds and hundreds of bytes in it because it has lots of things, many, many parameters, it can be faster to make it mutable, and then you're only really moving around pointers. In reality, I don't know how much it's going to matter. As always, I think with these, if you're talking about speed, it's best to measure things, okay? Because computers are so complicated and compilers are so complicated nowadays. Sometimes it's actually hard to reason about what's going on. There are tools in Julia. I very, very briefly shot through some of them last week where you can look at the compiled code and so on. It can tell you. And there are brilliant packages out there, benchmark tools and profile view, probably two I'd give shout outs to, that can let you see how fast things are and you can measure them and do it. But, you know, in your case, you could probably try it with them without mutable and just at time your simulation and see what happens. If you're really curious, that sort of thing, yeah. Okay, I haven't got any messages from the chat online. Okay, in the room, yes. Oh, sorry, yes, in the project too, yes. I should probably get up the project. Yes. Okay, the empirical distribution of the sojourn time of a job through the system varied as a function of lambda. So if you had, what do you mean? It wants an abstract vector. And what have you got your sojourn times as? A vector is an abstract vector, so that's, okay, maybe it was the type parameter of the vector, like it wants a real one or something. Another thing you can do here, just to give some hints, and is just to try and create a histogram. So if you have a vector of things, you can go using plots and then histogram it, and then you can visualize the distribution. Okay. Okay, so I didn't come up with the marking rubric, but I would imagine you would want something like a series of histograms for different lambda, so you can sort of see how the sojourn chain varies as a function of lambda. So you could look at the mean sojourn time, for example, you know, as a function of lambda, and that would be a line plot. But it's asking specifically for the distribution. So you have to sort of create some kind of empirical PDF out of the samples that you have. The easiest way to do it is just bin it and make a histogram, and it sort of looks right. So the histogram function from plots will actually bin it for you. Yeah. Otherwise, you just sort of create like a dictionary or something and you round it or floor it or seal it or whatever you want to the buckets of interest. So you can do it manually. It's not a terribly complicated algorithm, but I would highly recommend looking at plots.jl and the histogram function, because that will make your life easy. Yeah, so it's complicated, right? Because it's a history. You want to, the distribution also is a function of lambda. So distribution normally has, the variable of interest, the probability already, so it's 2D. And then it will also have another dimension for lambda, okay? So you could create a movie, like a 2D movie as a function of time. You could do a bunch of 3D plots, which, maybe they look 3D, or you have a top-down colored plot with time and lambda. Well, it's not time, it's, time, so doing time. And lambda, and then the color on the plot would represent the probability density. So maybe it's darker where it's more dense, more probable. Or you could just have a series of histograms. I mean, I encourage you to use your creativity, sense of design, and what do you think conveys the information well? Yeah. So if you look at the plots.jl, there's a bunch of recipes, a bunch of different examples on the web where you can see them doing different things. And I encourage you to play around and just have a look and see what you think fits. But, hint, hint, nudge, nudge, have a look at the histogram function. Okay, brilliant. Everyone else must be, oh no, we got one here online, Thomas. Excellent. Thomas says, should we try to make our first two plots smooth? Leave lots of lambda values close together. Doing so for larger lambda makes the runtime very large. Great question. Didn't the assignment tell you which values of lambda to use? Or am I incorrect about that? So lambda is the entry rate, is it not? I see, but I guess the more events there are, the longer. Okay, so you give them the time. All right. So again, if you're having real trouble running your simulation lots of time, I guess your plot will have to be sparse. So this is one of the things where quality and efficiency of your code trade off. The more efficient your code is, the kind of nicer plots, the kind of better results you might be able to generate. But Thomas, I'd just say, do as many as reasonable, or look at making your code fast so you can make it smoother. But I don't think, I'm not going to talk about the marking rubric, but I can't imagine we're hugely sensitive to the amount of lambdas you sample. Yes. Yeah, so honestly, I think this is, again, where it's best to use your sense of curiosity and math skills. Start with something like 1 and just see what happens, right? And sort of see, like, there's obviously going to be something we call small lambdas. If lambda is 0, there's probably not much is happening, right? But, have you tried it and see what the trends look like? Whether it saturates at some point, or I would encourage you to investigate. Probably a great question to put on Piazza as well, or consultation hour. Yeah. Yes. Okay, so really, I see, because there's a limit. How you write your simulation to handle this is sort of up to you. I would have read the assignment, and Yoni should correct me if I'm wrong. Please, Yoni. That there are, up to K people waiting in the queue, plus an additional person currently being served. That would be my interpretation. But again, this assignment has been written I found it very precisely. So I'd be surprised if this is not written here somewhere. Do you know where it deals with the queue size? Okay. Yeah, so again, there's more than one way to come up with the correct answer. So long as everything's consistent with your event and your state, it's fine by us. So the question is, like, should you include the person being served as someone at the station in the queue or not? And it really is up to you how you design your state and your process, just so long as it matches the model that we've given. I'm going to defer to Yoni and the tutors for that one. So the question was, how do the marks break down? Whether it's the plots or the code or what that's most important. Is there not any kind of description of that here? Marking criteria. Let's have a look. Okay, so 80 points for the simulation project itself, 60 points allocated for correctness of the results, for 20 for each of the plot types specified below. Okay, so clearly 20 points per plot, essentially. Well, they should have correct results in them. They should, be clearly designed. I suppose we want to make sure you have labels and units and these kind of things. Or maybe some of that's in this last 20 points for style design, code organization, neatness, sensibility of the output. Yeah. So, so that would be more, how nice and easy to read the plots are, rather than the correctness of whether you actually got the right result and whether it looks sensible. Yeah. Okay. No, that's all right. I'm sorry. Yeah. I can't be terribly specific on this because, yeah. Oh, you mean it's frustrating not to know whether the results you have are correct or incorrect? Yes. Yeah, that's how it is in the real world. I'm sure you can do some sense checks at certain values of lambda, like 0 and things, and make sure the simulation's working. Yeah. Excellent. I think we're going to move on. So for a few minutes, I'll just close this. Right. Okay. So Unit 7 is all about working with data, which comes in all sorts of forms, has all different data types, comes in all different file formats and stored in different places. We're going to look at how it's stored in databases, how typical databases operate, and we're going to play with some data sets. You got a data set we're going to deal with here. I believe I can't remember if there's a tutorial. And there's going to be a data set for project 3, okay? Which I'm not going to talk much about project 3 today because you've got your hands full already. So I'm going to speak for a few minutes about introducing data and databases, and then we'll come back after the break and we'll discuss dealing with data and data frames and this kind of packages in Julia. And I'm gonna do some analysis in front of you. And then we're gonna finish up with a bit of a discussion about big data and medium data and what can we do? What do we do when the data doesn't actually fit on our computer, okay? So that's today. And then after that, we're gonna move towards machine learning, okay? So machine learning is a complex term, is a fancy term to me. I think of it, it's a way of, usually it's a way of making a computer make a prediction or create some insights from some data, okay? Some people even go as far to call artificial intelligence, whereas that's probably a bit of a misnomer for the kinds of things we're going to discuss. But we're going to like see how to infer, how a computer could read handwriting, or we can see, and that kind of thing, okay? And we see how we can make predictions. Given some inputs, can we predict the outputs? But yeah, before that, we're going to talk about the data itself. So these kind of predictions are only really useful when you have a lot of data to sort of operate with, to make inferences on. All right. So we're not going to really touch databases per se, but you do need to know what databases are because they're very prevalent. And any of the data that you get given over your careers, if you're doing this kind of work that we're covering in this course, most likely it's come from, or potentially Excel or a SQL database, okay? So a database is a system which is designed for storing your data and accessing your data, okay? So a database is something which will make sure that if someone writes data to the database, that it gets saved correctly so that you can read it again later, okay? So a database is a complex system. It has to deal with the fragility of computers and this kind of problems. Like, you know, you could pull the power of the computer. You don't want your production database to kind of disappear. The most common sort of database used in industry is a relational database, okay? Which means that the data is organized into a series of tables which are related to each other, okay? And the only real common way of dealing with relational databases is through a language called SQL or SQL, okay? So, and SQL is not like any other programming language you've seen. It's a special case language just for dealing with databases. And UQ has courses on databases like INFS 2200 and more advanced courses. It's a fascinating and deep topic. There's also newer kind of things coming out of the computer science, data engineering kind of world, you know, cloud databases, you know, databases that span the world like Google Spanner and things like this. It's kind of very, very fascinating, rich and deep kind of area to study. So I just want to talk about relations, relational databases and SQL, and then we'll take a break, okay? So a relation is a mathematical term, okay? It comes from quite pure maths as a set over tuples, right? Or named tuples, and is a generalization of a function. So what's a tuple? So a tuple is just a set of things like X comma Y in Julia. Julia is great because if I go like 1, 2 like that with those brackets, that thing is a tuple with an integer and an integer, okay? Julia also has these things called name tuples, like A equals 1, B equals A, B, C, right? And the type of that thing is a name tuple. So tuple is just things. So, you know, a set of things. They might have names, like variables have names, like X and Y, okay? So consider a function Y equals f of X, okay? The names here are X and Y. Okay, we can think of this function as a relation. So it's a relation where, I might just move that down the bottom so we can see that in the room. Sorry, everyone else. So we can construct this relation. It's a set of tuples. So we can say that a tuple XY exists in this relation, defined by f, if and only if y is equal to f of x, okay? So let's say, you know, what can we say? Function, we can do this shorthand, f of what x equals 2 times x, right? So the sort of tuples that we could have is things like this, like so x, f of x for x in, say, 0 to 10 or something. Okay, so we can create a set of tuples, and a set of tuples is just a relation. Okay, the set X might actually be the set of all natural numbers, or the set of real numbers, or the set of strings, or the set of dictionaries from strings to integers. You know, it could be any kind of data type. Yeah. Okay. Okay, but there could be more complicated relations which are more complicated than functions. So a good example of this is the square root function. Okay, so if you have the relationships x equals y squared, you can solve that equation and come up with y is equal to plus or minus square root of x. But of course, this function, that solution, y equals plus or minus square root of x, if we're talking about real numbers, there is no solution for negative x. There's one solution for x equals 0, and there's two solutions for positive x. Okay, so it's not like a function at all. It's a relation. It's a generalization of a function where there could, at any given x, there could be any number of y's. There could be 0, 1, 2, 100, a continuum. You know, that's what a relation is. Okay, so the fundamental operation in a relation is set containment. It's a set of tuples. So the question you can ask is x comma y in the relation? That's the fundamental thing. Okay. And just like functions can have more than one input, relations can have any number of things in the tuple. A really interesting case to consider is the empty tuple. So the tuple of size 0. There's actually two possible relations in that case. You can have the empty set, or you could have the set containing the empty tuple. So even without defining any other data types, you've already got something, you know, non-trivial, where you can, for example, do a kind of Boolean logic with the empty relation being false and the true being represented by the relation with an empty tuple in it. Okay. But yeah, that's a bit of an interesting aside, I think. Generally, when we're dealing with relations outside of mathematical concerns in databases and things, the kinds of relations, the elements aren't like continuous real numbers or something. That, you know, these are discrete relations with finite numbers of sets of things in them. In other words, a relation is very much like a table. Okay, you can think of every part of that named tuple, you know, A, B, and C are the names A, B, and C of columns in a table, and the rows are the tuples that are contained in the relation. Okay, if it's truly a relation, then it's a set and the order of the elements don't matter, so it doesn't really matter what order the rows are in. And a row should be unique because it's a set. Now, sometimes relational databases will deal with bags, which means you can have multiple rows with the same data in it. So it's sort of a generalization, I suppose. Like, and you can think of a relation as a table like this with name, birthday, and is adult. Okay, so here's 3-column table. There's 3 people in this table with different birth dates, and there's this is adult column. Now, this relation actually happens to also be a function because is adult can be a function of birth date. Okay, but it's still a relation. And there might be other uniqueness constraints. There might be only, you know, one person of each name allowed in this table, or you might have a special ID column to identify each person in case people have the same name. Yeah. So, and when you have the unique constraints on a table, we generally call them keys. You can use the key to look up a row, and the primary way to look up a row, the most obvious key that you'd use to index your data, store it on disk, to get a row when you want it, is called the primary key. Okay, and it's an important term in databases. Generally, you know, like I said, we're going to have many tables. So let's look at a relational schema. So a schema is sort of the shape of the sets of relations or the tables. What's the schema for the tables in the database is the question. So there might be 10 tables. The first table might be called users. It might have the primary key user ID and so on, which we'll look at an example here. Okay, so basically we want to be able to tie, say, rows in this relation with other relations. And we generally use IDs and things to join data sets with other data sets. So just to give a taste or an example, here's an example of, it's not a real example per se. It's an imagining of how LinkedIn might store their data. Okay, so you all know LinkedIn. It's basically Facebook for resumes. So here's imagining an entry for Bill Gates and the kind of data that you might see on the LinkedIn website for Bill Gates. It has like a summary. It's got like the positions he's been in the past here, the educations he's had before, and so on. And the way you would store this in a relational database is each kind of part of this thing will come from different tables or different relations. So for example, there might be a table just for the users table. Each user might have an ID, a first name, a last name. This summary here that the user probably enters themselves could be a column of free-form text. And then there might be things like the region ID. Here it says Greater Seattle area, industry ID, photo ID. And these other IDs let you link to other sets of data because other people might live in the Greater Seattle area. And you might come up with a code for that so that, you know, for example, you can do a query and you can ask for all the LinkedIn users in the Greater Seattle area or all the LinkedIn users in the Greater Seattle area that, you know, are in my industry and things like that. Okay. So the way these tables relate to each other are through these ID columns generally, but it could be anything. And you can sort of see, like, for each user, we have a different table for positions. Each user might not have one position, but many positions over their life that they want to put on LinkedIn. So that's actually a different table where there might be multiple rows for the same user ID for the multiple positions that, you know, Bill Gates has held, for example. Yeah. Yeah, so for ID is really good because if two people are, say, born with the same name, you know, things are going to get pretty confusing. So, you know, you'll find you know, the government gives you a passport number and a driver's license number and things like that, tax file number, and that's how they track you. You know, when I was growing up, I had a Video Easy card number. You know, everyone wants to give you an ID of their own. Yeah, but generally, when you're creating one of these, it's good practice to separate the tables of different sort of cardinality into separate tables and to link them together through IDs. So, you know, this primary key is used as a column in this table, and you know, there's special words for this. We'd call that a foreign key. You know, that this table has a foreign key of the user ID of the users table. Yeah, this is from an excellent book. If you guys really get deep down into the data engineering databases and you want to know how they really work, how modern web scale, cloud-based sort of databases work, there's this excellent book by Martin Kleppmann called Designing Data-Intensive Applications. I should actually create a web link here that I recommend. We're actually at 6 o'clock, so I'll come back and we'll cover SQL and data frames together after the break. Yeah. Excellent, thank you. We'll take we'll call it a 10-minute break. I'll be back at 10 past. Thank you, everyone. All right. I'm going to call it 6:10. Welcome back, everyone. We're going to just briefly be introduced to the SQL programming language. I'll take this off because it's sort of annoying. And then march on to doing this kind of dealing with tables and relations in Julia. Okay. So SQL is an old language from 1973. It was called SQL until they realized that was trademarked by something else, and they renamed it to SQL. So some people call it SQL and some people call it SQL, depending on, I don't know, your preference, I suppose. It's an interesting programming language. It's quite different to what you'd see today. It's old and it's a different form. It's a declarative programming language for the most part, although it does have imperative components. So what declarative means is you write a query which describes what you want, and it goes away and figure out the algorithm for doing it. So you don't give it algorithms. You describe the results you want, and the database is free to find the algorithm. Okay, so in some ways this simplifies things, especially for beginners. You don't have to think about performance and this kind of thing. But yeah, so here's an example of a query. So select user ID, first name and last name from users. Okay, so it'll give you 3 columns from the users table, and it will give you every single row. Okay, so if it's a big table, it will give you lots of data. Normally, what you do is you have this as text, you throw it across a network connection to a database, and the database responds with the result. Okay, there are also local databases like SQLite that you could use on your computer, but you generally communicate with the database in real time in text, and it gives results back to you. That's sort of how SQL works. You can sort of refine this query to just get the user you want. So if you know the user's ID, you can get all their data directly. This is going to be a lot faster because the database just has to go to the table, look it up by primary key. It's already in a dictionary, so this is a very fast lookup. Autolog n in number of rows, look up, and then it returns just that little bit of data to you. So it's not too much work for you or the database. You can use joins to, well, I said we could, relate users to say positions. So we can get a list of positions and first names and last names, basically these things, by joining the positions table with the users table. Now, this is, there's a couple interesting things here. The user ID column exists in multiple tables, so we have to kind of like disambiguate which one's which. Doesn't really matter which one you put here, for example, but you have to specify something. It can't be ambiguous. Because of this relationship here, they happen to be the same number, but, yeah. The second thing is, if you have a large users table and a large positions table, this could potentially return lots and lots of data. Okay, so if you are LinkedIn and you wrote this query, you would probably break LinkedIn because those tables would have, maybe 1 billion users, and each person may have had 10 jobs or something. So the database will be scrambling around to join all this data and return it to you. It'll have to go over the network, which is very slow, and accidentally writing big queries on production databases can slow it down to the point that all the people trying to use the website, trying to do little single row queries, they can't do that anymore because the database is busy. Okay, so you can basically bring down entire apps and websites and things by making mistakes in your queries, which is kind of hilarious and kind of scary. Generally, you'd have something more specific in mind. So you want to show Bill Gates's page, you would join with the condition here on the thing. So this would now only return the 2 rows, the 2 positions Bill Gates has held. Okay. But we're not really going to use SQL in this course. I just want you to know it's there. I don't want you to be afraid of it. And I just want you to know it's very useful. Okay. A lot of data in the world is stored in these kind of databases. And, you know, you might find people keep giving you something like a CSV file or something. And eventually you're going to be like, well, where does that CSV file come from? So instead of harassing someone else to query the database, it's good to have the skills to do it yourself. So if ever you have the opportunity to learn more SQL, I just encourage it, because as a kind of mathematical kind of people who are going to be working with data throughout your career, it's just a good skill. Data frames. Okay, so see, Julia doesn't have a relational database built in. It doesn't use SQL. It doesn't have the concept of relations per se built into it. Generally in R, Python, potentially MATLAB, Julia, you'll use these things which are generally called data frames. Now that's really, to me, that's a fancy word for table or a relation, if you prefer. So each row in the data frame generally corresponds, you know, we're doing mathematical, scientific stuff. You generally think of each row as some observational fact about the real world. And columns, you know, they're for the different sort of features or attributes of that fact. So a typical row in a data frame is an item or an event or an individual. You know, we sort of know that. So the different columns, every item in a column will tend to have the same data type. Like the name column will always be strings. You know, the age column will always be a number, and so on and so forth. The date column, you know, date of birth column will always be a date. So yeah. So we're going to look at a particular data set right now, and we're going to analyze it using data frames in Julia. So there's this data file called athleteevents.csv. I've got it on my computer here. I think in this directory, athletesevents.csv. If we have a look at it, it's a 40 megabyte file. Yeah, we got this from Kaggle, and it contains all the athletes that have participated in the Olympics up to 2016. So it contains 15 columns of data about the athletes and 27,000 rows. Is that correct? I'll verify that for you later. I thought there was a few more. But anyway, that kind of data these days is small data. You can fit it in your RAM. But back in the 80s or perhaps 90s, you would have a challenge loading this data and dealing with it, okay? You know, my first computer didn't have a hard drive. The one that did only had a 40 megabyte hard drive. So yeah. But yeah, so this sort of analysis is definitely in the small data regime. We've seen how to look and open CSV files in Unit 3, where we looked at JSON and CSV file formats with Paul. And I think you probably use data frames.jl briefly for that, but we're going to take a deeper dive. So just to sort of demonstrate the things you can do with these packages and the kind of analysis we can do. Okay, there's different packages. Julia has data frames and type tables. In Python, you're going to use pandas. It's clearly the most popular one. In R, then there's, it has built-in data frames, and there's a competitive package called data.table that people use. Okay, so what we're going to do is we're going to imagine we're kind of just handed a data set, and we're mathematical people, and we want to sort of analyze it. So we're going to do something called data exploration. So we're given this file here, and we want to know what's in it. It's a CSV file, so we could print its contents. I'll even just do this at the REPL here. Oh, I don't need CSV for this, sorry. So I can just paste that in. It should, yeah. So it's printed out the first few lines of this file. the header row has the names of the columns, ID, name, sex, age, height, weight, and then it has all the data, okay? Didn't render too pretty on this HTML page, unfortunately. What we've got here is this do. Do here injects a function into open. And the way open is designed is that it opens the file, calls some inner function, and when that function either returns or throws an error, it makes sure the file gets closed. Okay, so this way you don't have open files on your computer and stuff. You're not wasting resources. You're not wasting RAM and things like that, even if things go badly. So you can't forget to close the file. So yeah, do here is just fancy syntax sugar. Literally, it creates a function which takes an IO, and that's the body of the function, and then it sticks it here at the beginning. Okay. That's kind of cool. So we can see what's in here. One thing I'd notice is that we see these things called NA here, not applicable. You know, these are columns where we don't know something. They're missing data. So we're going to load the CSV with the CSV package. Okay. And we're going to tell the CSV package that in this data set, NA means missing. Okay. So now Julia's going to load this file. It's pretty quick. I can kind of do this here if we like. You don't know if this data set's going to be available online, but you can go away and play with it if you want afterwards. It's definitely download it from that Kaggle link that's there. So here we're loading the CSV file at the REPL. Sorry, this is taking a second longer than I thought it would. Yeah, I was wrong. So is that 270,000 rows? Yeah, or 27,000, 270,000 rows. And it's sort of gone through this CSV file and loaded it from disk. And then we've gone through and we've converted that CSV file into it and put it into a data frame. So here, this looks like a table. It's got the names of the columns in this gray here that I'm not sure if you can kind of see. It has the type, and then has all the data here printed out with some of the values are missing. So some of the competitors, we don't know their weight or their height, for example. Okay, it looks like this data is sorted maybe by last name or something like that. Okay. With the data frame, we can do different things. It's a bit hard or intimidating to see it all at once. So you can use the first function to extract a few rows. This isn't useful just for printing, but if you're doing some analysis that takes time, you might want to just take a subset of your data and do your analysis on it, make sure it's correct, and then try and do it in the full data frame. So there's a last function, which helps you see the end of the data frame. Or you can index it. So a data frame, it's like a table. It's like a two-dimensional structure. It has columns and rows. Okay, so you can index, you know, the set of rows you want, the set of columns you want. And in Julia and Python, the colon here means get everything, get all the columns, or get all the rows. Okay, so this is get the rows numbered 1 to 10. If you want to get one of the columns, you go df.id, and that will return all that data as a column, as a vector. Okay. So you can think of all the columns of data frames as just arrays. And you can get the height one. Here we can see that some of the heights are missing, as we noticed earlier. And maybe we'll want to figure out what fraction of them are missing. So there's 60,000 missing heights out of 270,000 rows. So it's a reasonable fraction. When you're looking at real data, you'll find, you know, a fair fraction of it is corrupt or missing or, you know, something like that. And you can't just ignore the fact. It's not like one row out of a million is slightly wrong. It's like a third of your data is screwed, you know, and you have to deal with that. So the count function just returns and counts the number of trues. So how many of these is missing? Have you seen this piping operator before? I don't know if Paul demonstrated it. This basically just takes the output of this thing and pipes it into that function and then evaluates that function and returns it. So it's just syntax sugar for that. Okay. we might want to know how many distinct athletes are there. So one thing we noticed is the athletes were kind of repeated, like Christine's here like 5 to 6 times and so on. So we can use unique on the data frame, and we can tell it which row or column, sorry, to makes the row unique. In this case, it has an athlete ID column. And what it does is it just keeps the first row with that ID and throws away the rest. Okay, so we're going to get a smaller data frame with only 135,000 rows. So roughly on average, athletes compete in 2 events, I suppose. That tells us, because there were 270,000 rows in total. And now we only have 1 row per competitor. So before, the multiple rows are because, you know, someone might do the 100-meter freestyle, the 200 meters freestyle, and the, you know, 400-meter medley, and so on. And they might compete in multiple games or multiple years. That's why people were repeated. So let's just do a few simple analyses of this. Let's see how many men are there. What's the gender balance? There's 100,000 men to 33,000 women. So historically, it hasn't really been very close to 50-50. So what we've got here is this is a count function. It takes a predicate function. So this itself returns a function, which when you compare it to something, it gives you true or false, whether it's M or not M. So this is counting the number of things in the athlete data frame .sex column. How many of them are M and how many of them are F, okay? And we get those 2 numbers. Now, if we had lots of different groups, we wanted to look at how many people were in each of the games or something like that, how many people competed each year, we'd have to do a calculation for each year, right? And that'd be kind of annoying. So there's this package, I'm a bit biased towards it because I wrote it, called Split, Apply, Combine. It has a few useful functions for grouping data in vectors, basically. So here you have this function called group count. There's a more general group function which does more general things, and you can group this column, and it will immediately tell you how many M's and F's there were, how many male and females. But we can group by the team, which is the country in this case, and we can see all these different teams. And it's sort of a dictionary going from, you know, country name to the number of elements. Now, if you really want to, one of the best tricks when you're exploring data is to sort it, okay? So here there's these ... So we might be missing something important, you know, some country that's 10 times the size of China. So we could sort it by team size, and we actually can get it here. So here we got United States are the most prolific sort of competitors. And, you know, Australia's actually pretty far up the list given our population. As I mentioned, group is a more general version of sort of like group count. So this it's probably a little bit hard to see here. That's kind of the row there. It's giving you, say, all the names of the competitors for. So we're grouping team and name here. So team is China, and this is an array with all the different competitor names. Okay, the same for all the countries. And then down the bottom, we've got, so there are a lot of weird things with Olympics and politics and wars and stuff where you end up with these weird teams. Yeah. Okay. Now that's a function that you can use with any data. Like you don't need to be working with data frames. It's just a general thing you can do in Julia. The data frames package has its own functions for dealing with data frames. So on one hand, it's kind of annoying because you have to remember multiple kind of functions, group and group by and things. And on the other hand, it's really, really convenient because those functions work really well with these tables, with these data frames. Okay. I should point out that there's this cheat sheet here. There's a link in the things. It gives you all the various different kind of things you can do with a data frame. So I'll point that out again later. So here we can group the athletes by team. And what it does is it's created a group data frame with 1,000 groups. Okay, the first group is China. Here are all the rows for the Chinese competitors. All right, there's a whole bunch of other groups, another 1,000 groups, and then the last group was called Mainz. It's interesting. Mainz had one competitor. This is called a group data frame. So it's like a collection of data frames, sub-data frames, right? You can combine each data frame into a row or a set of rows with this combine function. And so it takes this group data frame, and we're just going to count, for each group, we're going to count the number of rows, the n row as a function, and we're going to convert that into the count column. Okay, so I'm going to explain this arrow and this colon and stuff in a few minutes, but basically you can, get your data, split it apart into groups, and then, analyze each group. So in this case, just the number of elements, the number of rows, and spit out a result. Okay. So as I said, that's some fancy syntax I'll explain just after a segue here. Okay. Before we go into more dive of how to use these data frames, let's understand what they are. So effectively, they are a table, so they contain rows and columns. But the way it stores it is it stores each column as its own vector. Okay, so it's very much a column-oriented data structure. You can get one of those columns quickly with dot. Okay, so it's sort of like internally, it's kind of like a dictionary of columns. So if you go dot height, it finds the column called height and then returns that. And that's relatively cheap, but you do have to find the height column out of the other 15 columns. So it's not exactly free, but it is cheap. But that vector is stored as a Julia vector. It's dense in memory. It's very fast to operate on that vector by itself now that you've got it out. You might also not consider columns. You might want to consider each row. So there's this each row column for data frames, and you can look at the first row. And what Julia's had to do to create this, or you could index the first column. We saw the indexing earlier. It gives the same result either way. To index this, to create this thing and print it out, what we've had to do is we have to go to all 15 column vectors and find that element of that index and then extract it and then put it in the row. Okay, so this is like 15 times harder than it was to just extract the column. Okay, so this data structure, because it's column oriented, it's going to be faster to deal with entire columns of data at once rather than one row and then another row and another row, because it's just going to take the computer less work. Usually when you're doing analytics, you really, when you're doing one tiny little step of your analytics, you might only involve a couple columns, right? Your entire calculation might use most of the columns, but when you're doing a little step, you're doing a group or something, you might just be creating an index on one of the columns or two of the columns, not like all 15. Of course, there are other data structures you could use where it's stored as rows so that the row access is fast and the column access is slow. Okay, and that's perfectly fine. SQL databases typically do this because when you're using a SQL database, it's like LinkedIn. You want to look up that one user and you want to update their date of birth or something. You just want to deal with one row at a time. And because the main value in a SQL database is to be able to do these nice transactions, to be able to persist data on disk quickly and without faults. They tend to be in this row format. Okay, but more modern analytics databases might exist that do it the column way, which might let you do big queries really fast, but it would do transactional stuff slower. So it's all trade-offs, right? Do you want columns or rows? It's just a trade-off. So if you want rows in Julia, perhaps the easiest way to do it is just to create a vector of named tuples. Okay, I spoke about named tuples earlier. So, I could create a table which is like, name equals Alice, age equals 42, name equals Bob, age equals 13, and so on. And that's a perfectly legitimate table, right? I can get my table, I can get the second row, I can, get the age of the person. You know, I can do all the things in Julia with that data structure. And that's fine. If you don't have any packages available or you just want to do something really quick and simple, it's perfectly fine to use a data structure like that, okay? And it will be fast enough, right? Like if you're dealing with small data, it doesn't matter if going by columns is 2 times or 3 times faster sometimes, right? You just want to get your analytics done and move on. There's another package called type tables. Again, I'm biased because I wrote it, but from that, you can create tables. This thing is also like an abstract vector. So it's a 1D container containing 1D rows. A data frame is more like a 2D container containing cells, okay? So there's a little bit of a difference in how you interact with it. But the type tables, they store it as columns, but you interact with it as if it were rows, okay? Really, there's millions of different ways of doing very similar things. There's query.jl. And for your work, you know, the data preparation work in Project 3, feel free to use the approach you like, okay? In the lectures, I'm going to double down on data frames. It's definitely the most used package, well-known package. So yeah. As I mentioned earlier, there's a really nice cheat sheet here. If you are going to use data frames, I highly encourage you to download this sheet. You can even print it out and laminate it and stick it to your computer if you want. But it will tell you all the little tricks of how to get rows and combine group data frames and do all the two joins and all the different things. Okay, so it's a really, really neat kind of cheat sheet, and it can be a good way because, you know, there's just a lot of functions to kind of memorize and stuff. You don't want to memorize them. You just kind of want to look them up when you need them. Okay, so data frames are constructed pretty easily. You just throw a bunch of columns at it like this. Okay, and the way the columns are indexed, you know, you just get them like I showed you before with the dot, which is gets a property. Okay. So you can, you know, create new columns by setting properties. So now it was a 2-column table. Now it's a 3-column table because I defined C. Now the column is indexed with this thing. This thing's called a symbol. Okay, it's like a string for the compiler. This is how the compiler knows, you know, your module is called base or your type is called float64. Okay, it's a string the compiler sort of interned and it's keeping it inside itself. It's actually stored in a sort of hash mat or hash set internally, and they never go away. Yeah, so if you can actually index a data frame with a normal string, but this is a symbol is actually a faster way of doing things, and it's the way it deals with code. The compiler deals with code. And in fact, that syntax df.c is sugar for get property function, you know, df of c. Okay, just like the square bracket indexing is sugar for get index. It's exactly the same sort of pattern or idea. Okay, again, you can use the colon, for example, to get all the elements of the column C, which is just the same as doing df.c. That you can you know, get certain subsets of rows and columns and things with indexing. In Julia, it has a filter function, which means given a set of elements, apply a predicate and return the collection with just the things where the predicate returned true. Okay. So one thing you often want to do is filter down your data frame into a particular set. So maybe you want only the rows where the height's not missing, or only the rows for females, or only the rows for the 2016 games or something. So you can, for example, we had this data frame had, I think A was 1, 2, or 3. We're only looking for the rows where row.a is an odd number. Okay, and you can do that. Now, what this will do is for every row of the data frame, it will go and construct that row, data frame row with all the columns. And And then it'll go row.a, which will have to do this kind of search. Which column's A again? Find it. And then it will call it isod, okay? So there's a lot of bookkeeping going on, iterating a row like that. And it's actually a lot faster if you kind of know that this is a column-based data structure, and you tell data frames to first get the A column and then put it into this isod function. Now, this symbol here creates a pair. It's usually used key value pairs in a dictionary. They've just used it as a convenience. It looks really pretty. It looks like A is going into isod, okay? It looks like the piping operator. It looks like the little arrow function thing. So it's just, this thing you'll see all the time in data frames, this kind of putting symbols into functions, into symbols and stuff. It's just a way of telling it which columns you want and where they need to go. And this will make your program like 100 times faster than this one, okay? So there's a reason why they have this sort of bespoke, interesting, weird syntax, but it's a bit unfortunate it's necessary at all, but it does make things faster. You can kind of think about filter in terms of indexing. In Julia and Python and R, I think you can index with trues and falses to keep certain elements in an array. So if you call isod on each of df.a, you'll get like true, false, true. And then you can index with true, false, true, and all the columns, and you only get columns rows 1 and 3. Oh, sorry, that should be isod there, but yeah. So that's a two-step process, right? So we find, you know, predicate for that column, and then we index with the corresponding things. Sorry, that should have been isod. In SQL, we had this select thing, which let you query certain columns and even make transformations on columns. So there's something similar here. You can just select columns A and C, for example. And then there's transform. Transform's like select, but it's like keep all the columns and add another one, okay? So we can transform the data frame, and we can take the B column, we can find the mean of the B column and stick it in a new column called mean B, okay? So B was 2, 4, and 6, so the mean is 4, and it's stuck it in every row, okay? So this is kind of useful because, maybe later on you want to divide B by the mean of B and have some sort of normalized B or something like that, okay? So when you're putting B into here, this is, like I said before, now it's a whole of column operation, which is why it can be fast. It's not like a row by row thing. It's like, oh, here's the column, there's a transformation on it. If it returns a scalar, it'll just copy it everywhere. If it returns another column vector, it'll just put it beside. Okay. I'm just going to run through quickly. The other really cool thing is group by. So this is going back to what we said before. You can group a data frame by a certain column, and then you can combine the result. You can take the sums of things. You can join strings together. This is string join. So here we've broken it into even and odd groups. So this is the even group where this A column is 2. This is the odd group where A is 1 and 3. And then we can, take the sums of the B's and join the C strings, and we end up with interesting things here. Okay, it's just a demonstration. Here's inner join. I'm going to skip over this because we're not actually going to use much relational joins in this thing. But just like in SQL, you can take multiple tables and join them together based on data in certain columns. Okay, this is what I really wanted to talk to about. So this is where I wanted to get to. So we're going to demonstrate the usage of these tools right here. So still too low, sorry guys. All right. So we're going to look at the height of athletes in this data set, and there's some interesting things going on here. So let's look at the male versus female competitors. So on average, you'd expect the males probably are likely to be taller. Here's a bit of an oops. If I just try and find the mean height, I get missing. So if there's missing data, it tends to propagate and pollute the results. So what you need to do is use this skip missing function as your friend. It takes like a vector, And it makes a vector without the missing stuff. Okay, and then you can do mean on that. Okay, so the mean height of the males that we know the height of is 179 centimeters, and for the females, it was 168 centimeters. Okay, so the males are taller. Now I want to ask a more complicated question. How has athlete height changed over the years, over time? Does anyone here think it might have changed or might have stayed still? Remember, this competition started 100 years ago. Yeah, so because of nutrition and various things, people are actually taller now than 100 years ago. Okay, so let's go and prove it. Let's look at the data. So let's look at the height as a function of year. Okay, so first, we want to, instead of doing this kind of group by group analysis here, let's do it with the tools of data frames and do the split apply combine strategy with group by and combine. Okay, so we get the athlete data frame, we put it into groups by the sex column, and then we combine them back together into a new data frame where the height has been transformed to mean. This is the functional composition operator. And then by default, what Julia will do is munge the name. So we're putting it back into the height column. Okay, so these are the results from before. The males are 179 centimeters, the females 168 centimeters, fine. Now let's do this not with sex here, but with year. How has this changed over year, height by year? All right, so, and then we're combining them exactly the same way, and then I'm doing a plot. And what we see here is a bumpy line. It's not going up, it's not going down, it's just bouncing around. So here it's sort of saying, okay, the competitors in the Olympics are probably the same height as they were 100 years ago, which is interesting. And the other thing we see is that on the left here, it's kind of wiggling slowly, and then on the right here, it's getting all jaggedy. It seems a bit weird, right? That seems very specific. So there's actually a few confounding factors in this data set, which is making this line a bit odd, and we're going to figure this out. So first is this jiggles are coming every 2 years, and that's because at a certain point in time, they offset the Winter Olympics from the Summer Olympics by 2 years. It used to be in the same year, and then it was in between, okay? So if we split into year and season now, we get two lines, one for the Summer Games, where it sort of stayed flat, and one for the Winter Games, where again, it sort of stayed flat. But we might guess that the Winter Games people are a bit shorter, okay? Now, if you want to compare basketball players versus jockeys, horse riders, you know, the average height of those two groups of people is quite different, okay? It's an advantage in basketball to be tall, and it's an advantage if you're riding a horse to be very light, okay? So you tend to get small jockeys. Now, I don't know much about all the different sports in the Winter and Summer Olympics, but generally we see a trend that the Winter Olympians are a bit shorter than the summer ones. And that's what's explaining these jagged up and down, up and down, up and down here. Okay, every 2 years it's going winter, summer, winter, summer, winter, summer. Okay. That's a bit more sensible, but there's still another thing going on. So women have actually become a larger fraction of the competitors at the Olympics over time. Okay. So if we split by year, season, and gender, we actually end up with a much more telling picture. It's the same thing. We've got summer female competitors in blue, summer male competitors in red, winter female competitors in green, and winter male competitors in pink here. And all four of these lines are going up. Okay. So this is interesting. So now that we've sort of used the tools and we've split apart the data, now we're starting to tease out the true relationships here, okay? So things were kind of being hidden. You know, I find this really interesting. Things were kind of being hidden. My hypotheses here is on average, people were born shorter. They grew shorter because of mostly nutritional type of changes. Perhaps also sport has become more elite and competitive, so only the best at the sports get in, so you have to be tall to be a basketball player now, whereas maybe 50 years ago you didn't. But the big thing that's really explaining the results here is probably number 3. Women competitors have become more prevalent over time. and reducing the average height of all competitors. And a similar thing with the first graph. I think the Winter Olympics has also grown over time, and the Winter Olympians were a bit shorter. So we can look at number 3 here and verify it. Here we've got what I've done is we're creating the fraction of people whose sex was F, okay, and plotted that as a function of year for the summer and winter games. And now we can see with both the summer and the Winter Olympics, they both started out entirely male and have grown to be not quite, but closer to 50%, so 40% female now, okay? And it's because of this trend that these correlations, which are going up in this graph, a good 5 centimeters. So people are a good 5, or at least competitors are a good 5 centimeters taller. Why this graph looks so flat in the beginning, where, you know, you couldn't say that this was 5 centimeters different to that on the right, okay? So I don't know, that's kind of interesting. So this is how you kind of use these tools, and this is how you do data exploration, okay? You know, we've been plotting means this whole time. It's often really, really beneficial to think about distributions. So perhaps if we plotted the distribution of heights, we would see 2 peaks, one for males and one for females. And then looking at the distribution could ask you, you know, guide you to questions. It's like, are there actually multiple populations making up this data set? You know, should I tease them apart and look at them, those populations separately? There's lots more we could do with this one data set. If you have time and the interest, I'd encourage you to download it. You know, you could look at, I could think of lots of things, like how does team success relate to the socioeconomic status of the country that people come from? How does, what about the team success relate to the distance to the Olympics? I remember when Olympics was in Brisbane in 2000, there were a lot of Australian medals because basically there were a lot of Australian competitors. Because everyone could afford to travel to Sydney, whereas most people would probably drop out otherwise. You know, we'll probably see the same thing in 2032 in Brisbane. And this is the one which really is leading into our next lecture. Can we predict how well a team will do at a given Olympics based on the data, like the socioeconomic status of the country and other data about the country's population, these kind of things? Is it possible to make a prediction? Like, we generally know that in the next Olympics, I'd expect, you know, America and China and Germany and Japan to do well because they have in the past. So, but, you know, how can we create, you know, a better predictor than just rough feelings, you know, for how things might turn out? And machine learning is one way of doing that, is you take a data set and you try and figure out, get it to determine the correlations in the data so that it can make predictions for the future for you. That's the purpose of something like machine learning. Are there any questions on this segment? Or online? Okay. So, when you're looking at project 3 in the future, you're gonna start with a data set, and then you're gonna do some machine learning on it. So you're gonna have to use tools like these to load the data and to put it in a form ready for the machine learning model. Okay, so, you know, come back and review the lecture or the lecture notes. Look at the data frames, cheat sheet I gave you, or just type you know, dataframes.jl into Google and look up the documentation. Same for csv.jl. If you're having trouble, you can just encourage you just to look what's there and to use the documentation. You're going to need to use that for project 3. Cool. I want to spend the little bonus 10 minutes. Well, we don't even have 10 minutes, sorry. Part of this lecture to talk about memory management and big data. Okay. So, again, this is more to explain and give you context about how this works in the real world rather than, you know, assessment-based kind of learning. When we're dealing with data, we can generally categorize it into one of three different sizes. The easiest one to deal with is small data. Small data will fit in the RAM of my computer. Okay, now this depends on how powerful my computer is. You know, you can get computers with 128 gigabytes of RAM, which is going to be better at handling that kind of data than a smaller computer. And that's what we're doing in this course. We're not going to push you into these bigger kind of things. But just to know that they're there. There's something I would call medium data. Medium data is not really I don't know if it's a really well-used term, but I'm going to use it here. Another way to think of, people call it out-of-core analytics or this kind of thing. There's various words for it. But basically, your data doesn't fit in your RAM, but it will fit on your hard disk. So your hard disk might be, you know, several terabytes big. Or if you have a server, it might be, you know, 100 terabytes, big hard drive, okay? So you might be able to fit an entire, say, SQL database for a large business on a server, but you couldn't fit that SQL database into RAM on that server. And so this is the niche that, well, I hesitate to call it a niche, the area where SQL databases have dominated. They really deal with the fact that not everything's in RAM. The data's so large that we can't just regenerate it again from scratch. Like, let's say you're doing some calculation, and to do it with all your data, it might take a week. What you're going to need to do is you're going to have to, you know, your analysis or whatever you're doing that takes a week, you're going to save it. You're going to have checkpoints. You're going to have lots of little steps, and after each step, you're going to save the data to disk. And if, you know, the power goes out, you need to be able to turn your computer on and resume what you're doing. With a SQL database, if someone writes a row to the table, you know, that row better be on the disk when you query it again next. You don't want something to have gone wrong, okay? If something goes wrong, the client that wrote the row needs to be told, oh no, sorry, that went wrong. Can you try again? So that they can deal with it, okay? So there's actually a lot of additional complexity here with this size of data, where you have to deal with the fact that, you know, everything needs to be persisted on disk safely, and you know, file systems are weird on computers, and there's lots and lots of things going really strange here, and it really amps up the complexity to have to do this. The way you deal with, say, a calculation, analytic style calculation, is you would do it in mini batches. So if you have a CSV file that's terabyte, you know, many gigabytes, you might load 10,000 rows from it, process them, and then save them to disk, and then load the next 10,000 rows, process them, and save them to disk until you get to the end, okay? This way you won't explode your RAM, but you will eventually get to the end of the file. Yeah. So, and then there's something called big data, which is probably a term from the 2000s onwards, which is data which is too big to handle on one machine, okay? It's not going to fit on one hard drive. It's petabytes. It's just not even feasible, even if you had a very powerful computer to deal with it. So generally for this, you're going to have a distributed system. You're going to have many computers in a cluster, or you're going to have many computers in the cloud, or you could even be many computers all around the world talking together, working in unison. So if you're a mega company like Google or Facebook or LinkedIn, you're going to have, you know, a global network of databases serving out this data, and it's not all on one computer. There's going to be many databases talking to each other, storing the data, fetching the data for other people. Okay. When you work at any time, when you're working at scale, it's business as usual for a computer just to die. Okay. A hard drive to get corrupted, your RAM to get corrupted. You know, a cosmic ray can come in to the CPU and flip a transistor at the wrong moment, and your calculation can come out wrong. Okay, so your data or your calculation could be wrong at any moment. And when you have millions of computers, this happens every day. Okay, so if you're Google or Amazon or something big, you have to worry about this. But even companies I've worked for, where we only had a couple petabytes of data, we still had to write the system to be fault tolerant. Otherwise, you know, if you had to start from scratch every time something went wrong, it would be impossible. We'd rent fleets of computers from Amazon And, you know, occasionally one would die and we'd just have to restart that calculation. And, you know, maybe some other computers have to wait till they're done before they do the next thing or something, but it all had to be accounted for. You know, things could die, things could go missing, things could die without you knowing that they died. They could just, you know, you think they're running, but they just never finish. You know, anything could possibly go wrong, okay? Dealing with this scale, though, has become a lot easier because of the cloud. Not only does it mean you can just rent your computers, but they provide a lot of services. I'm thinking AWS has this thing called S3. It's like a giant hard drive. It stores your data in triplicate in 3 different buildings. So even if like a meteor hit their data center, there's 2 other data centers with your disks, for example. So yeah, at that kind of scale, if you want to guarantee things are working, you've got to do some pretty big engineering. Generally, if you're going forward in life with the kind of content in this course as a data scientist, you're going to be spending, or you or your team or your business or your organization is going to be spending about the same amount of effort doing the data engineering as they would the actual science and analysis and machine learning and sort of this deeper stuff that all you mathematicians are really good at. You know, there's going to be at least as much effort spent on just making sure the data's there and you can get it and you can save it. And there's a computer for you to run your calculation on, right? There's a lot of that. And these 2 fields, they data engineering and data science, they overlap quite a lot. And you can kind of, as your career progresses, you can, you know, it's another avenue for you to, you know, to explore. There's many different possibilities. With the kind of skills you guys are developing. So I was going to use the REPL to sort of show an out-of-core algorithm, but given it's 7:01, I'm going to skip that. Thank you very much for your time, and I hope you enjoyed the lecture, and we'll be back tomorrow to introduce machine learning. Hey.